if I can. All right. What we're doing today, guys, we're getting into contingency tables. And contingency tables is pretty much like we did last week. However, one of the things that you guys might have realized last week when we did them is they called it a, hold on. It was actually called a goodness of fit test, right? And it had one factor, and it was referred to as a one-way test. And that's because, not in terms of like a one-way test and a two-tailed test, but that's because we only had one factor or one variable. We were talking about things along the lines, I forget the examples from last week, but it was only variable, it was only relevant for tests of make sure they're independent, consistent with whatever hypothesis we want, but when we had one factor. Now, what we're going to be doing today is we're going to be sitting back and expanding on this just a little bit. The difference between 11.1 and the difference between what we're going to be doing now is we're going to have the full name is called contingency table, is how we refer to what we're doing, but it really is the chi-square test of independence. Let me make this a little bit bigger so we can see it. Independent, right? And the difference between this is that we're able to have two factors. And we would, of course, call it a two-way contingency table. So that's kind of the reason why we call it a contingency table, because we're trying to see that those things are contingent on each other. They're not independent. They somehow relate to one another, right? So 11.2 is essentially 11.1. I guess you could kind of say on steroids, just because instead of looking at one variable and looking at observed and expected and getting the value of chi-square, we're going to be doing tables that are a little bit more complex. As a result, we'll call them contingency tables. The test is not goodness of fit. Now it's called chi-square, but I will tell you, when you look at the little modification, it's the same thing. We're not using one factor. Of course, we use two. And if anyone were to be all fancy, it has been referred to as many people as the two-way goodness of fit test, right? That's what the one-way and the two-way refer to. It talks about how many independent variables or how many factors you're looking at. This is really bugging me with my camera. All right, so I'm going to clear this out. I'll leave it at the bottom for a little bit. I need an individual to read what's on the screen right now.
I'll read.
All right, thank you.
We now consider methods for analyzing contingency tables or two-way frequency tables, which include frequency counts for categorical data arranged in a table with at least 2 rows and at least 2 columns. In part 1 of this section, we present a method for conducting a hypothesis test of the null hypothesis that the row and column variables are independent of each other.
All right, let's stop right there. I want to make sure that we can digest what we've said so far. It's a lot, right? We are now considering analyzing contingency tables. I mentioned that before. It's listed right here, right? Or, like I said before, two-way frequency tables, right? I've seen them referred to as, in this textbook, there's two-way frequency tables, but I've also referred them as two-way goodness of fit tables. But either one would work, right? In the past, it was just one-way frequency table. Now we're doing a two-way frequency table, which really, we have 2 factors, 2 variables, right? Now they're going to include frequency counts for categorical variable. Remember, I told you, this is what makes the chi-square test of independence and also the goodness of fit different from everything else that we've done. Now we're referring to categorical data. Categorical data is data that has It's numerical. We can sit back and say, you know, true, false, or we can sit back and refer to a person's ethnicity. We can refer to their race. Whereas before, if you calculate the mean of somebody's race on the data, it would be meaningless. And I'm going to go through that just really quickly, just to show you what I mean by that. Let's imagine we got a survey, right? And we have persons saying that they are Black, white, and we'll say Latinx. I should have typed that up, right? Now, we put this information in the data point. We're going to enter this data into our spreadsheet, and we're going to give Black a value of 1, 2, white a value of 2, and Latinx a value of 3. Now, in this survey, just to make sure that we are moving with this example, we're not going to have an other, we're not going to have all, I'm just creating 3. Don't come at me, Dr. Barnes, there's other ethnicities you forgot. I know, right? Now, if we calculate these values, right, of putting them in for 1, 2, and 3s, now SPSS or any software that we did, we actually can sit back and calculate the mean, right? Let's say the mean is 1.25, right? What the hell does that mean? It means nothing. Now, what you might be able to say is that if this is a little number line, right, you might be able to argue that there's more Black people that were in our sample or people that reported as being Black in our sample because the value is really close to 1 and then the 0.25, but we wouldn't be able to say anything about how many Latinx people or Caucasian people were identified. So this approach is meaningless. I mean, it really means nothing, right? But what we're able to do with what we're doing with these contingency tables and these frequency tables, then it's appropriate. Because what we can do is we can sit back there and we can have our data listed in certain ways where we have, let's say, race listed. And we got B, W, and we got L, right? And then we got a certain, I'll say a frequency right here. We have the number of people who said they were Caucasian, the number of people who said that they were white. We could do a, like last semester, we could do a, not last semester, last week, we could do a goodness of fit test to find out whether there's a difference, whether we think there's more Black than white or Latinx at our campus. We're able to do that. But realize these are categories, right? Which is very different from what we've been doing in the past. Even though we can make this survey item look the same when they're looking at it and give it a value of 1, 2, 3 when we're entering in the data, calculating the mean on this means nothing. But doing a one-way frequency table or goodness of fit test, or doing the contingency table or the two-way frequency table that we're talking about today, we actually can make some sense out of it. Now, we're going to graduate this week because instead of just having one factor like race, we can also have more complex tables. Our tables that we're able to talk about today would not just be one row. We could have a factor here. So let's say factor 1, and that could be race. And then we could have factor 2, which let's say is income. You might say make a lot, a little, or not enough. We're going to do those aspects. And I also want to be clear that this, I don't want you to think that race has to have 2. We actually could have 3 races, just like we have right here. So we could have a 3 by 3 table. That's what this would be called. This would be called 3 by 3 table. If we only had these cells, that table would appropriately be referred to as what? What do you guys think that table would be?
2 by 2.
All right, a 2 by 2. Excellent. Right. So let me sit back and let's do this. What if we were to have all that? What would that table be?
2 by 3.
All right, exactly. So you guys understand that. It's going to be really key to making sure that you understand what these tables are looking for. But this is a 2 by 2 contingency table, a 2 by 3 contingency table. And of course, we have it all highlighted, which we don't yet, but I'm about to get there. That would be a 3 by 3 contingency table. These things can get complex. They can definitely get complex. But I just want to make sure we understand that terminology of all of them. All right, so let me clear this, get this stuff out of the way. Then we can get back to reading. All right, which include frequency counts of categorical variables arranged in a table that has at least 2 rows and at least 2 columns. So that's the smallest that we can be. A 2 by 2 is the smallest, right? In part 1 of this section, which Jasmine already said, we present the method for conducting a hypothesis test, right? In part 2, we'll consider 3 variations, and I'm not going to talk about these in class, but they are on the reading handout, and they will be on the, what do you call it? They'll be on the exam, the math exam, and they will also be on the handout quiz. But it's really about making sure that you're just familiar with the definitions and know what they mean in the unique situation. We're not going to be doing math on these more complex versions, but we are going to be doing the math on the versions that are addressed in part 1. Do that right now. Okay. Definition, we have that right there. Actually, I'm not really going to go into the slide. I want to get into what we really want to do today, right? Here's a key. I actually think I should make this a little bit bigger, just so it's on the screen. The terminology is the same. I'm going to show you from what we did last week. We had O representing observed frequencies. Last week, we had E representing the expected frequency. Now, how we find the expected frequency is different. The assumption is the same, found by assuming that the row and the column variables are independent, but the equation that we're going to use is going to be very different. So we want to make sure we do that, and I hope we're going to listen and pay attention while I'm going over it. Now, in order to support the way that we do the expected values being a little bit different, we need to be familiar with this terminology, right? And I was just talking about correlation coefficient in my last class, and R would be the correlation coefficient. But in this chapter, 11.2, R does not represent the correlation coefficient. R represents the number of rows in a contingency table. The number of rows in a contingency table, right? The next variable that we need to have and think about is C. And if R equals rows, I'm betting and we're sitting back there realizing that it equals the numbers of columns in a contingency table. And this is very important because you need to make sure that we're always keeping things the same. I want to show you 2 examples of contingency tables. This right here is a contingency table. And here's another contingency table. Now, in this example right here, how many rows do we have and how many columns do we have? And then in this example, how many rows do we have and how many columns do we have? See, it's kind of scary.
Which one?
Yep, go ahead.
The first one is a 2 by 3 and the other one is a 3 by 2.
All right, a 2 by 3. 1 row, 3 columns, 1, 2, 3. Rows, we have 1, 2, 3, and then columns 1 and then 2. Absolutely. Now, essentially, they will have the same number of cells, but you need to make sure you keep this information straight, right? There's no shortcut for understanding or knowing what a row and a column are, right? So I'm glad I did this, especially since we didn't have people jumping at sharing the comment. All right, let me go over here, annotate, undo the last couple of things. It's probably better to erase it. Boom. Okay, now there are a couple of requirements. One of the important requirements that we do for this, it's true almost for everything, almost everything we do in the stats class, we assume that the data has to be randomly selected, right? That's almost a given, but we are going to go over it and talk about it today, right? So one of the things is to make sure that your data is randomly selected. You can't go around and pick like a sample that's completely biased and you sit back and think that these results are going to work. The sample data are represented as frequency counts. Each cell will be like a frequency, right? In a two-way table, right? Two-way is not saying 2 by 2, but it means it has two factors. And those factors can be anything. It could be a 3 by 3. It could be a 4 by 3. It could be a 4 by 5. I don't want to get that complex, but they at least have to have a two-way table, which means it's referring to two different factors. Right? And then here's the key, which I'm going to make this highlighted red. The expected frequency is at least 5, right? I'm going to highlight this. It's referring to the expected frequency. That's not the observed frequency. The observed frequency is you go out there, you record data, what's in there. No. We're talking about the expected frequency, right? So what is the frequency that we would expect using the equation that we're going to be talking about shorter? There's no requirement that every observed frequency, that's pretty much what I said. I didn't even read it, but it's right there. So the expected frequency, when you calculate them, that's when you want to double check and make sure at least every expected frequency equals 5. Now, I mentioned the way that we're going to calculate the expected frequency is a little bit different. So I'm going to show you how it's different, and we're going to do some examples. All right, now the first thing we want to do right before we get into that is looking at a couple things. Again, the row and column variables are independent. It's how we're going to write our null and our alternative hypothesis, right? Our null and alternative hypothesis are always as follows. There's not much variation right now. I know in the past, for the goodness of fit, we could have gave any of those values, any frequency that we wanted to, and we did sometimes, especially on this past Monday, we did that, right? But it's not that same. It's not the same flexibility. When you're talking about a contingency table, you need to sit back and say the row and column variables are independent. And then you'll say the alternative hypothesis is that the row and column variables are dependent. That's the only two things we have with this basic approach. Now, I kind of jumped forward, right? But we wanted to make sure that how do we calculate the expected value? The way that we calculate the expected value, which is a little different, you need to multiply the row column times the column, the row total times the column total. And then we're going to divide that by the grand total. Now, what I mean by that is this. Let's imagine we have a table that looks like this. This is the value of A, B, C, we'll say D right here, E, and F. Now, these wouldn't really be letters. They'd be values, frequencies, right? But if I'm doing the row total for an expected value, let's say I want to do, I'll do this in green. I want to get the expected value of this right here. We are going to take the row total and multiply that by the column total. Now, how do we get the row total? The row total is going to be D plus E plus F. Right? And then the column total would be A plus D. Now, what is the grand total? The grand total is really just going to be A plus B plus C plus D. Oh, my handwriting is real bad. Plus E, and then plus F. All right, so let's do it again. I'm going to figure out, let's figure out, we're going to do the observed value for B. All right, I need a volunteer. What values will be my row total? What will I add up for that row total?
For B,
For B, yep.
A plus B plus C.
A plus B plus C, all right? Somebody else. What would be my column total if we're doing the expected value for B?
B plus E.
B plus E, all right. I like this. You guys getting this. All right. I'm going to do another one and ask for some other volunteers. Let's do the expected frequency for F. What would we add up?
C plus F.
All right. Now, I asked for row total, but if you were getting column total, you'd be right. So let me do C plus F. Right. So that will be right for that. Now, somebody else now give me the row total if we're doing the expected frequency for F. Got 9 people in the
F plus E plus D.
F plus E plus D. I think that's what you said. I don't know why you went backwards, but
Yeah.
it's the same thing. It would be D plus E plus F. But since adding them, it doesn't matter. You're right. We can go D plus E plus D at the very thing. So I'm just going to highlight this right here to show that it's the same, right? Those are the values. Now we could go on doing the others, but I think you guys got it. We got some participation. So let's move on. The next thing I want to focus on is how to get degrees of freedom. We're going to use that same table in the back of the book, but to get the degrees of freedom, we're going to use this. It's going to be R minus 1 and then times C minus 1. That's going to give us the value of our degrees of freedom to use on that table. Now, this is the kind of stuff that when you read, it's in the book and you can take note of it. You can take note of it. All right, so let's move on. Okay, I'll go over this. What I'll say is this really quickly. Now, usually when we're doing all the rejection hypotheses in the past, I always draw a normal distribution, and then I'll sit back and show you like, look, this is where we want to have the line, and our rejection region will kind of look like this, right? And if it's in that rejection region, we reject the null, and if it's not, we'll say that we failed to reject the null. Well, if you were to draw a normal distribution for the goodness of fit and or the test of independence, it's actually not a normal distribution. It actually will look a lot like this. It's skewed. So the value will look like this. It always, all the values have to be positive. There's no such thing as a negative chi-square value. If you got a negative chi-square, you did something wrong, something very, very wrong, right? So all positive, I'm gonna put that right there. All positive values. The same logic, however, works. You know, you sit back and you find out what the critical value is, and then you will reject whether it's independent, or you'll fail to reject whether it's independent if it gets into the critical region, or if it does not get to the critical region, you fail to reject. Same logic, but technically the distribution is not normal. And I'll be honest, I think on many occasions I probably have drawn, because I'm sketch labeling in shade over here, I've probably drawn this and I'll probably continue to do it. Now, it's not going to matter, right? It's not going to matter to you, but technically, if you want to follow the rubric and follow the way that it works, it should be a skewed distribution like this, as opposed to a bell shape, which we've done so many times. Okay. What I want to do is I want to sit back and we're going to do the math for each of these. Now, the answers are actually up here, which is, actually, I'm going to take them away and make them disappear. And I'm also going to take away these. So we can do the math. We can find them out. Okay, now, what I want you guys to do, and I want you to, chat should be very active if we're doing this right. I want you guys to calculate and give me the 2 row totals. Now, in order to do the row totals, what you need to do is the row total for together or alone is, to get the row total, you got to add 236 and 133. That'd be your first row total, whatever that value is, put it in the chat. And then also do it for 54 plus 77. All right, that number looks good to me, Deja. Good job. Now that's 1. That's only the row total for row 1. Let's get the next row total. All right, all right. All right, Nyrese, that's 1. Jasmine, good. All right, now we're going to switch focus to the column totals. Actually, I can't do those numbers as easily in my head. All right, I'm getting both values now. They're all looking good. I did get a 310, although I think that, yeah, that person, there was a little typo. Excellent, excellent. All right, I think everyone who's trying to be engaged and trying to demonstrate is getting correct answers. I don't think I'm going to wait too much longer. All right, so with that being said, I'm going to sit back and erase these because we all got them. We know what they are. I can erase what I kind of hid right here. Those values. Excellent. Now, the last thing is doing the column total. And I don't want to waste time waiting for that. So I'm just going to do this. Now, what you'll do is you just sit back and add up all these values. 236 plus 133 plus 54 plus 77 should equal 500. However, I want to show you guys a neat little way to make sure if you're doing these things right, and it is kind of handy. 290 plus 210 should equal 500. 369 plus 131 should also equal 500. So if you are doing these values and you got them written down, a nice little double check is to add the values here and to double check the row totals as well as the column totals to make sure that those values all equal 500, to make sure all of them equal 500. All right, now what's next is we want to calculate the expected frequencies. Now I'm going to do this together with us. The expected frequency for this right here is going to be the row total, I'm going to say RT, times the column total divided by the grand total, right? That translates to, write this in 369 times 290 divided by 500. I'll put that right there. There we go. Now, I would love for you guys to do that value and put that value in the chat. All right, now I'm looking. I actually can't even take it off the screen without y'all seeing it, but it looks like I got 4 answers and they are all the same down to the second decimal point. So either we have 4 people who miraculously did the wrong mistake or the same mistake, or you guys got the right answer. And I'm going to bet that you guys did the right answer. All right, so annotate. Let me get rid of this. Let's see what happens when we get rid of it. Boom. Excellent. Now, I'm going to pick another one of these at random. Let's do the expected frequency for alone and poor standing. I'm going to go down here to text. In order to do that, we need to have the row total, which is 131, times the column total, which is now 210, divided by 500. All right, looks like I got my first value in here. Well, we got a couple of them. Never mind, y'all fast. Okay. Now it looks like it's 4 responses. I'm not going to say it's the same 4 responses. Let me see. Yes, it is. 5 responses now. All right. Okay. Yeah, a lot more people in the class. All right. Again, I'm not going to wait longer than that. Again, we either got 3 people who are doing this and all are doing it right, or they got the wrong answer and it was down to the second decimal point. Thank you guys. You guys are absolutely right. So let me get rid of these. These are the expected frequencies, right? They're all visible. Now, I want you to realize it's a lot that we've done right now, right? What we'll be doing next is we're going to sit back and do the contribution to chi-square. Now, I told you guys before, this is key. I got something else in the chat. Let me check it out. All right, excellent. Okay, kind of a late introduction, but that's good. That means you're with me. All right. Now, what I'm going to be doing is trying to sit back there and show you guys how to do the chi-square. Demonstrate the equation for each of the chi-square unique contributions, right? Now, in order to get the chi-square from this, we would essentially have to get the chi-square contribution for each of these cells. These numbers right here are referring to, I'm sure you guys can see it, but I just want to make sure it's clear. This cell. You'll see that the 54 is the observed from here. That's when they did it. They had 500 people. That's how many actually said they were alone and in good standing, right? 75.98 is the expected frequency, right? So if those things are independent based on how many people were in the rows and the columns, that's what we would expect. And at 75.98 corresponds to this value. This equation that we're doing is exactly what we did before. It's from what we did from the previous chapter. It's observed minus the expected squared divided by the expected. The only thing is that in this chapter, we are calculating the expected in a slightly different way. The equation that we're using for our expected is not what we did. The last time it was just like, look at it and put the number in there. This chapter, it's just a little bit different. Okay, now it looks like I think Deja went ahead and solved this. I'm not 100% sure, but I think she gave us the value for this in the chat. At least she gave me, I'm not sure if it was to everybody. But when on the test, I will be asking each of you, when I talk about the unique contribution towards chi-square, this is having a step that's not in a textbook, but it is saying, okay, looking at this cell and this cell alone, let's do the observed minus the expected, square it, and then divide that. And that value would be the unique contribution to chi-square from this cell. When we take the observed minus the expected here, square it, and divide it by E, that's the unique contribution for this cell. The quiz, there's for the math exam, this honestly, I think I pushed D2L to its max, because even though I can sit back and do D2L and it can have different numbers each time a quiz is taken, I can't do it in a way that you can do a problem 6 different times with the same numbers. So I need you guys to understand what this unique contribution terminology is. When I'm saying unique contribution, I'm asking for one of these particular cells. Calculate what chi-square would be using this equation. Now, when I ask you for the total chi-square, that's when you would get the unique contribution from all of these cells, add them up, and that will be the equation. Ooh, hold on. And that would give us chi-square for all of it, which equals the sum of the O minus the E squared divided by the E. And that's you're adding all these up. That plus this equals that. What time is it? All right, I'm going to clear this drawing. Let's get out of here. Let's go to this handout that I created. And it really should be getting you guys halfway to where you need to do for another one of these handouts. Handout 11.2. Ooh, wrong handout. It's the wrong handout too. Hold on. Here it is. Okay. Now, this right here is the handout that, since we know what we're doing here, I think no one's going to have any problem with it, right? But again, this is a table. Now I'm going to ask Nyrese. Nyrese, you were good at this earlier. What type of contingency table is this? Is it a 2x2, a 1x2? How will we describe this contingency table?
4x2?
4x2?
No.
Yeah.
No, wait. Yeah, that's what I'm going.
Yeah. Don't let me discourage you sometimes. A 2x4, or we could say a 4x2. I think 4x2 is actually the appropriate way. I don't think there's a rule, but yeah, I like 4x2 because you said it. I don't want to go against what you just said. Right? Now, you look at this, all these items right here kind of numbered, and these numbers are how I'm going to grade this assignment when you do it. You're going to need to print this out. Some of y'all might be savvy and can go into, I know the browser I use is, right now I'm using Microsoft Edge. And when I use Microsoft Edge, I'm able to add notes to this document, right? And I know some of you have been handing your homework in that way, right? But I need to do a couple things. Each of these numbers right here, 1, 2, 3, 4, 5, 6, that's how I'm going to grade this assignment when I get it in the submission for you. And it will ask you questions on the handout. So all of these aspects that have these numbers 1 through, let's go all the way down, 20. All of these questions right here are reasonable things that you can expect to have to answer when you're taking the quiz for handout quiz 2. This is handout 2. Let me just say it again. Handout 2. Right here. And of course, there's a handout quiz as well. But if you go through and you answer these questions, like if you calculate the row total, right? I'm going to do it in my calculator real quick. 67 plus 91, that's 158. So if I print this out and write it, or if I do it on the screen, right? Or if I add notes from the software that we have right here, it will allow you to do the answers, and you'll be well prepared for this. 44 plus 18 equals 62. Right? Calculating the grand total. I can put this number here. When you print this out or do it in Excel and do it writing on with notes and you have access to it, you will be able to do the handout quiz for 11.2 very easily. Trying to do it in real time would probably be a headache, but I would encourage people to go through. We already went over what the hypotheses are. The hypotheses are basic, right? It's either they are independent, the factors are independent, are not independent.
That's the actual hypothesis.
Yep.
Okay.
And again, that they're always the same. The last time I used to be a little bit more fancy. You could sit back and have the specific values, but for the contingency table, when we get this complex, that's the hypothesis. It will be this way anyway. The only way you could change it is if you want to say the names of the factors. Like if you look at it right here, we could say, I actually don't even know what this is about. Let's scroll up and look at it. But I don't know whether males or females, the relationship between males and liking particular artists are independent, right? So you could change the word factors to be exactly what the thing is talking about. All right. Same thing, it's doing 2 examples. This right here is asking you to calculate the expected frequencies. We did that already. No one is, I think, going to be struggled with that. 16. I want you to calculate the 8 unique contributions of the chi-square. Degrees of freedom, critical value. Again, reading and what we did in class will allow us to do that. And then, ooh, I just said this. I said draw a normal distribution. Check that out. It's not a normal distribution. You guys know it should be a little bit skewed like the example was, as opposed to a normal. Now, whether you do normal or skewed, it really doesn't matter, because at the end, you're going to have a critical value. So you have a critical value at the end of a skewed one, or you'll have a critical value at the end of one that's normal. I'm not going to take off points for that. I do not think it matters. It's really about a visual way to find out whether it's you should fail to reject a null or not. That's the other assignment for handout 2. Both of these are up on D2L. Good luck. We're 2 minutes past the end of class. As a result, I'm going to stop talking, stop recording.